Hi Dashers. I'm under a time crunch, so I hope you'll forgive me. And we will go over some of this in class, some of these math problems. So I'm going to kind of fly through and hope that you can pause this video when you need to. So today's notes are on 9-2 and 9-3 about how Newton's laws apply to a group of particles, and then also just the concept of momentum. So they first want, because we just went over center of mass, they want to make sure that you know that we've been, up until this point, we've been talking about how does one thing move usually. So, but Newton's second law still applies to a group of things, and you can take that object, that set of things, and look at its center of mass, and as long as that group of objects is not affected by a force outside, and it's not losing mass in any way, it's not gaining or losing mass, then it's still gonna obey Newton's second law. So there's just these reminders here that, F net, well, and actually, it's okay if there are external forces as long as you know what they are. But the mass has to be constant. You can't be losing any mass or gaining any for this period of acceleration. And then the acceleration that you would be finding would be the acceleration of the center of mass for this system. So for a few examples here, we would be thinking about, like, for instance, that pool ball example. When you think about from, as the cue ball, the white ball, is moving toward there, the cue ball is moving, right? So, but it's got let's say, a constant velocity, so it's not accelerating. And then when it hits the rest of the billiard balls, then it's going to transfer some of its momentum, but that whole system, okay, is still not going to have any acceleration. As a whole, it's going to move, but its center of mass is going to maintain this velocity it had before. Assuming, like, that basically, like, there's no friction with, like, the tabletop and it's rolling, and we haven't gotten into rolling yet, but okay. So another example are, like, a classic example are fireworks, and the fact that when these fireworks are launched, they're a projectile, but you can predict the path of the fireworks center of mass even after they explode, because you know that that acts still like a projectile. So that lets you predict where that firework is going to land, what's left of it, or all the pieces are going to center around that spot, okay? Because you know the acceleration of that is going to be due to gravity. That's it for projectile motion. Okay, so in class we're going to do a couple examples here, because, like, in this case you have an object where it's not accelerating at all. It started off not moving, and so then since all the forces are, like, internal, then it must not be, the center of mass is not moving it, throughout that example. Okay, so we'll do that in class. We can also do one of these projectile motion examples as well, so we know what's gonna happen to these pieces, because we know where the center of mass should be. Okay, and then the idea of linear momentum is not complicated, okay? It is mass times velocity, and therefore momentum is a vector. It has the little arrow symbol. It is given by the variable p, not sure why. And its units are kilograms times meters per second. There's no special unit for it. And so this concept, right, is that the more mass or velocity something has, the more momentum it has. And the way you would change something's momentum is by applying a force to it over a period of time. And we'll get into that more. But another interesting thing, okay, is that we can reimagine net force, because we know like net force is mass times acceleration, right? But acceleration is the first derivative of velocity. So really, since mass is just a constant, you know, then you could pull that out of, you know, the first derivative of momentum, and then you kind of realize, oh, well, then force is just also is like the derivative of momentum. And this is actually how Newton originally wrote his second law. So he did not write it as acceleration is net force over mass. He wrote it like this. So it's the rate of change over time of momentum that is equal to the force on an object. So it's like saying, okay, if I'm gonna try to change this object's momentum at a certain rate, that's how I'm gonna do it. I'm gonna put a net force on it. Okay, so please try this checkpoint 3. It's in your book if you didn't do that already. I think that's going to be pretty simple for you. And then they also just wanted to point out that if you're, again, talking about more than just one thing, you know, all the billiard balls or the firework, okay, that also, of course, you can have the momentum for the whole system of particles, and you would just take their mass together, multiply by the velocity of the center of mass, and there you go. You'd have that momentum for the whole system. Okay, that's enough for today. Thanks.